Okay, good afternoon, everyone. So today we're going to finish up talking about earthquakes, and then we'll talk a little bit about the exam that's coming up next week. I've posted a lot of information about that on Blackboard, as well as practice exam questions and study guides in the form of the learning objectives. So after we finish up earthquakes, we'll talk about that, and then we'll just get a little bit of an introduction to rocks and minerals, which is what will be our topic for the next couple weeks after that. Okay, are there any questions before we get started? Okay, so at the end of class on Wednesday, we were talking about earthquakes and how geology can help us assess the risk posed by earthquakes in a particular location, right? So we had talked a little bit about generally what earthquakes are and what causes earthquakes, and the fact that where we can define earthquakes are in these different tectonic settings that we talked about when we talked about crustal deformation. This is like continental collision, convergent margins, continental rifting, and transform boundaries. And then the last thing we talked about was how we can think about the likelihood of an earthquake happening in the relatively near future of the next few decades by thinking about the recurrence interval, right? So just as a reminder, recurrence interval is the time between earthquake events, and I'm not going to go through all of this again. I just want to kind of remind you of where we were last class. And this is also something you looked at on the exercise that was due yesterday. So if there are any questions about this, I'm happy to kind of go over some things again, answer questions, but otherwise I'll move on to the next thing. Okay. So generally we said that the shorter the recurrence interval is, the more frequent earthquakes are in a given area, right? So over very long timescales, hundreds or thousands of years, you're likely to have more earthquakes the shorter the recurrence interval is. And another thing that can affect how likely an earthquake is in the relatively near future of the next couple decades is how long it was since the last earthquake, right? So remember from our elastic rebound theory that as the plates are kind of constantly moving, but the fault is locked, stress and strain is building up on the fault, and it gets more ready to slip and cause an earthquake, right? So the longer it's been since the last earthquake relative to the recurrence interval, the more likely you are to have an earthquake relatively soon, right? And so that was one thing you looked at on the exercise, was you calculated the recurrence interval along this segment of the San Andreas Fault. And then you thought about, well, how long ago was it when the last earthquake was, and how does that compare to that recurrence interval? And is it likely that there's going to be another earthquake relatively soon? Okay, so let's have a little poll everywhere question to think about the likelihood of earthquakes. And so again, when we're talking about the likelihood of earthquake, it makes a difference, kind of the time scale that we're thinking about, right? So whether we're thinking about hundreds of years or the next few decades or the next month might make a difference. So this question says, which fault do you think would be most likely to produce an earthquake within the next month, and why, right? So the question itself you don't need to answer why for this multiple choice question, but I want you to think about that. So the choices are a fault with a recurrence interval of 100 years, and the most recent large earthquake occurred 50 years ago. A fault with a recurrence interval of 200 years, and the most recent large earthquake occurred 300 years ago. Or a fault with a recurrence interval of 200 years, and the most recent large earthquake occurred yesterday. So go ahead and answer that poll question, and then we'll talk about it a little bit too. So it looks like most people have answered the poll question. If you haven't, go ahead and submit your answer now, and we'll take a look at the responses. Okay, so 82% of people said a fault with a recurrence interval of 200 years ago, and the most recent large earthquake occurred 300 years ago, right? So the idea here is that it's the average time between earthquakes is about 200 years, right? And so it's been longer than the average interval between earthquakes. It might be that sometimes it's 200 years, sometimes it's 400 years, sometimes it's 90 years. It's good. There's going to be some variability, but just thinking about the fact that this stress is building up on the fault, since it's been quite a bit longer than that average time, it's pretty likely that an earthquake will occur soon. Now, it turns out this is actually a little bit of a trick question because it says within the next month. So if the question said within the next, if it said specifically produce a very large earthquake within the next, I don't know, 20 years, I would probably go with answer B, but actually the correct answer is C, right? Because this is actually not a question exactly about recurrence interval, but you also think about aftershocks, right? So when we talked about, when we watched that animation of the really big earthquake in Japan, and then you see all these earthquakes that happen after that, when there's a really big earthquake, within the next few weeks or months, it's likely that there's going to be more earthquakes, right? Which could be very large earthquakes or could be smaller earthquakes. But so it was a little bit of a trick question, but those of you that chose, actually all of these choices were pretty reasonable things to think about, right? The first choice, if we're looking, it again depends on the time scale that we're looking at, right? So if we're like, which of these faults has the highest risk of earthquakes over the next 100 years, it might be A. If we're looking at the next 20 years, probably B. If we're looking at, as the question actually said, in the next month, probably C, right? So it's just designed to get you to think about all these different aspects of kind of the probability of earthquakes contributing to the risk. Okay. Okay, so any questions about recurrence interval or anything else we've talked so far about earthquakes? Okay. So we've so far been thinking about things that are going to affect the probability of an earthquake happening, right? Now we want to think about if that earthquake happens, what are the effects going to be, right? So both of these things, the chance of it happening and what the effects are if it does happening, are contributing to our overall risk from that natural hazard. Okay, so essentially the way that earthquakes cause damage is that they cause the ground to shake. That's what an earthquake is, right? And so we want to think about how much the ground is going to shake and how much energy is being released by that earthquake and traveling out in these seismic waves, right? So our next question we're thinking about in terms of understanding the science of earthquakes is what determines the intensity of that shaking? And more generally, how do we quantify the size of an earthquake, right? A bigger earthquake can potentially cause more damage. And so when we talk about the size of an earthquake, usually we're going to be talking about what we call magnitude. And this is it relates to how much energy is released by that earthquake. So when an earthquake occurs, right, we're breaking rocks along the fault that releases energy that travels out as seismic waves. And so there's, obviously the more energy that's released, the more potential there is for damage, depending on some other factors as well, right? So a lot of people have heard of the Richter scale, right? And this is what was used several decades ago. This would be the main thing that we used, and it's based on the amplitude of the wiggles on a seismograph, right? So the stronger the shaking, the bigger the wiggles are. And so what they would do is they would look at the amplitude of this S wave wiggle, and also know that, if you're closer to where the earthquake occurred, it's going to be bigger wiggles. If it's farther away, they're going to be smaller. So you can normalize for that distance. And for many different seismic stations, you can calculate the magnitude based on that. And so you end up with one magnitude for that earthquake, right? Because it's giving the proxy for how much energy is being released. What we use to measure and report the magnitude mostly these days is actually what's called the seismic moment magnitude. And this is rather than just being based on the amplitude of the wiggles on the seismogram, it's actually based on more complex modeling of these seismograms that allows them to actually calculate characteristics of the rupture on the fault. So both the area that ruptured along the fault, how much slip there was on the fault, and then also taking into consideration kind of the strength of those rocks that were breaking. That's going to enable us to calculate the amount of energy released and then assign a magnitude based on that. And both of these Richter's magnitude, moment magnitude, for most earthquakes, that number should be about the same. The reason that we use the moment magnitude now is that the Richter magnitude actually, when you get to really large earthquakes, ends up underestimating the amount of energy released. So really large earthquakes, you might have a slightly different number for those, but for the most part, they're about the same. And these are both logarithmic scales, which means that for each kind of step up in the magnitude scale, you're releasing multiple times the amount of energy. Okay, so let me kind of illustrate that. We'll come back to intensity in a moment. So we're going to talk about magnitude, which is related to how much absolute energy is released by the earthquake. So again, magnitude is that energy released, and it's a logarithmic scale. So for each step, as we go from a magnitude 6, magnitude 7, magnitude 8, it's releasing 32 times as much energy, right? So I have a demonstration of this, right? That we can use an analogy of breaking a piece of spaghetti for rupturing a fault, right? So let's say breaking one piece of spaghetti is equivalent to a magnitude 6 earthquake, right? Which is a pretty big earthquake, moderate to large earthquake. And so, it takes some amount of energy to break that piece of spaghetti, right? Now, when we move up to a magnitude 7 earthquake, right, it takes 32 times as much energy, or 32 times as much energy is released by that earthquake, right? So I have 32 pieces of spaghetti now, and so it takes 32 times as much energy for me to break that spaghetti, right? So a lot more energy released by our magnitude 7 earthquake than by our magnitude 6 earthquake. Now, if we move up to a magnitude 8 earthquake, right? This is now 32 times as much energy as our magnitude 7 earthquake, which is about 1,000 times as much energy as our magnitude 6 earthquake. So I have here approximately 1,000 pieces of spaghetti. I actually ran out of spaghetti. It's probably more like 900 pieces of spaghetti. But so it would take a lot more energy to break this. And someone said in the chat, can I even break that? We'll see. I'm pretty sure I cannot break it just with my hands. I don't know if I try my leg. Yes, I can, but it was very hard. So, so these bigger earthquakes release a lot more energy is the take-home point here, and make a really big mess on my desk too. Okay. A lot of spaghetti on the floor. Yes, I am going to, well, not the ones that ended up on the floor, but the ones that ended up on my desk, I will cook and eat. I just the last, probably a few weeks ago, I finished the half pieces of spaghetti from this demonstration from last semester. So I will eventually eat all the spaghetti. Okay. And with these earthquakes, even a magnitude 6 earthquake is releasing a lot of energy, right? It's not just spaghetti that we're breaking. A magnitude 6 is equivalent to one atomic bomb, like the type of bomb that was dropped in World War II. magnitude 7 would be 32 bombs, magnitude 8, 1,000 bombs. So this is a lot, really huge amounts of energy that we're talking about. Okay, so that was magnitude, right? So that's energy released by the earthquake. And then when we're concerned about the actual damage that happens at a given location, even more important than the absolute magnitude of the earthquake is how much shaking is going to happen at that location, right? And so to describe the amount of, or the intensity of the shaking at a given location, we use what's called the Mercalli intensity scale, right? And so this, this map on the right here is the, is mapping out the intensity using this Mercalli scale, where different colors show how intense the shaking was in those different locations, right? So the orange colors are very strong shaking, the green colors are moderate shaking, the blue colors are weak shaking, right? And so as you can see, compared to the magnitude, which is there's 1 magnitude for that earthquake, the intensity also depends on where you are, right? And so they measure this intensity by basically after the earthquake happens, they go around and they interview people about how intense the shaking felt to them. Was it enough to wake them up if they were sleeping? Were things falling off the walls? They look at buildings and see how much damage there was to buildings to get an idea of how intense the shaking was. So I want you to take a second and look at this map and think about what is affecting the intensity of shaking. There's generally 3 things that the intensity of shaking depends on. Does anyone want to take a guess at what some of those 3 things are?
Proximity to the epicenter?
Yeah, exactly. So we can see the star is showing where the epicenter of the earthquake, right? This is that 2011 Virginia earthquake. And so we can see that we have the highest intensity closest to the epicenter. Clay.
Does altitude affect it?
Can you say that again?
Does altitude affect it?
So altitude, not directly, but topography can play a role in kind of focusing the energy in certain locations. So you're kind of on the right track there. Orion?
Would the material of like the earth there also impact that? Like if you have a more like dense packed rock in like the bedrock as opposed to like less dense?
Yeah, exactly. So the material does affect the amount of shaking, and that's the main, besides the distance, the main thing that's affecting this is kind of the material and some of the fabric of the rocks and the structures in that area that might direct energy more in one direction than another. So we can see that it's, if we look at where the kind of moderate shaking happens, it's not a perfect circle, right? Because we might have certain areas that have more softer sediment and other areas that might have more hard rock that affects the intensity of the shaking. Rachel.
Could the general preparedness of like population haven't prepared for earthquakes or like
So Rachel, you're breaking up. I might have gotten the gist of
it is going to be your buildings are going to be like.
So your connection was breaking up, but I think the gist of what you were saying was that since the intensity depends on, we determined by looking at the damage to buildings and people's perception of how intense the shaking was, it might depend on the types of buildings that they have and whether those buildings shake more easily and get damaged more easily. So I think, yes, that could have an effect. For the most part, I think they try to correct for that in assigning the intensity. So it shouldn't be something that's actually determining the intensity of shaking, but it could affect, the data. It could be a source of error within the data. So, well, one other thing we can think about, it's maybe not so clear from looking at this, just the pattern on the map, because this is from one earthquake. But as I said, this is the Virginia earthquake from 2011, and it has some information about the earthquake. It was a magnitude 5.8, right? And we can see that near the epicenter of the earthquake, this corresponded to, I guess, very strong shaking according to this scale, right? So one other thing that the intensity of shaking depends on is, of course, the magnitude of the earthquake, right? So depends on the magnitude, the distance from the hypocenter, right? So we can't see this on a map, but remember the hypocenter includes the depth of the earthquake as well. So earthquakes that occur closer to the surface of the earth are going to have more intense shaking at the epicenter than an earthquake of the same magnitude that occurs deeper in the earth. And then the type of rock or sediment making up the ground surface can cause what we call amplification of these seismic waves. And so yes, Lily.
I'm just confused how the intensity of shaking is different from magnitude.
Yeah, so magnitude is the amount of energy released by the earthquake. So that energy, so when you break the rocks, that releases energy, and then that energy travels out as seismic waves. And so there's a certain amount of energy that's released by the earthquake, and that's related to the magnitude, right? And then the intensity is at a given location, how strong is the shaking, right? So if you're closer to exactly where the earthquake occurred, that shaking is going to be stronger, right? For a given magnitude. If you're farther away, that shaking is going to be less. And then there's also, as we said, the type of material that's making up the ground can also affect how strong that shaking is in that location. Okay, so how the material making up the ground affects the intensity of the shaking is through amplification. So as these seismic waves travel from solid rock into softer sediments, the seismic waves slow down, right? Remember that the velocity of seismic waves depends on characteristics of the materials, including the density of the material. So when it travels into sediment, it slows down, and as it slows down, the amplitude increases, right? So this is showing, in rock we have this smaller amplitude, in the sediment we have this larger amplitude. So this is what's known as amplification, right? And this can be a really large effect. So the map in the lower right-hand corner shows the LA basin, right? So this is a sedimentary basin with a lot of sediment, and then there's these mountains to the north of that. And so we can see that relative to the mountains, the amount of shaking in the basin might be 5 times as strong because of this amplification effect of the seismic waves traveling through that sediment. And so if we have this amplification that causes more intense shaking, it can contribute to causing more damage in a location. So this other image is showing a picture from Nepal, Kathmandu, where Kathmandu itself is built on top of a lot of sediment. So it used to be thousands of years ago, there was a lake there that dried up, and there's thick sediment there that causes a lot of amplification, and that's part of what contributed to the huge amounts of damage in that area, in addition to the buildings, these buildings not being reinforced for earthquakes. Yes, Rachel, you have a question?
Yeah, why would the waves traveling more slowly increase the amplitude? Like why is that the cause and effect? If that makes sense.
Yeah, so as the waves slow down, you can kind of, this probably isn't technically right, but you can think of it this way: as they slow down, they kind of pile up, and the amplitude increases that way. Yeah. Okay, so it seems obvious that one way we can cause damage by an earthquake is shaking, which can cause buildings to collapse. But there's other things that can happen during an earthquake that can cause additional damage. And so we're going to look at some of these specific individual hazards that include ground shaking, but also what's known as liquefaction, landslides, and tsunami. Okay, and we're also going to think about the geology, underlying geology of an area, including the material that's there, the topography, the types of faults, and how these all might contribute to perhaps increasing the risk of these particular hazards. So the first thing we'll look at is the direct effects of the earthquake itself, right? So when an earthquake happens, a fault ruptures, right? And sometimes this rupture goes all the way to the surface of the ground and ruptures the surface. And that can cause damage to any structure that happens to be lying directly on top of the fault, right? So this is a photograph of, we have a road and a railroad that are going across this fault that has ruptured, and you can see that it breaks apart the road, right? Most structures aren't built directly on top of a fault, and so usually the damage that happens isn't from the rupture itself, but from the shaking, right? And so that shaking can cause buildings to crack and cause buildings to collapse completely. So sometimes seismologists say earthquakes don't kill people, buildings kill people, right? Even if you had really intense shaking, if you're out in an open field, you're going to be okay. You might fall down, but you're not going to be killed by an earthquake unless something else happens, like a building collapsing on you. So this picture on the right is just showing kind of different ways that buildings and roads can collapse due to shaking. And this is, you know, when people are trying to engineer safer structures, they need to take into account these different weaknesses inherent in the structure and how they can correct for that, right? So this top one's illustrating these kind of unreinforced, soft lower stories of a building that can just kind of collapse like a house of cards. The bottom one is masonry, so bricks, things like that are not good for earthquakes generally. They don't absorb that shaking very well. Anyway, just some examples. So the shaking itself can also trigger additional hazards, right? So one of these is what's called liquefaction. And so this is basically when the shaking causes wet sediment to go from being solid ground to acting like a liquid, right? So what happens is you have sediment that has water in between the grains of sand or whatever kind of sediment it is. And when you shake that, right, the sand grains kind of get suspended within that water and they lose contact with the individual grains. And so now that sediment has no cohesion at all, and it can just act like a liquid, basically. So let's look at a couple videos of liquefaction, just to get an idea of what this is. The other thing I'll say that this is analogous with if you've ever gone to the beach and you've gone down to the edge of the water where there's wet sand, you kind of step your feet on top of the sand. Eventually it gets like runny and your feet can sink down into the sand. It's the same kind of phenomenon. So this is some footage from the 2011 earthquake in Japan, the Tohoku earthquake. And these are a little loud. Images of liquefaction. And so, so what you can see is that the water that was in the sediment kind of got loose and in some cases made its way up to the surface and is, you can see this kind of muddy water pouring out onto the surface. And now the ground itself is acting like a liquid. And so you can see the way hedges in the middle of the road are kind of bobbing around. That's because the sediment underneath it is experiencing liquefaction and it's acting like a liquid, basically. And so here's another clip of this sediment-laden kind of slurry of water and sediment pouring out onto the surface. Okay. And there's a lot more footage there, but that's just to give you an idea of what liquefaction can look like. And this on the top right is kind of a photograph of what the ground might look like after liquefaction has occurred. So that water full of sediment that's pouring out of the ground then leaves behind these big piles of sediment that kind of make a mess. So in this diagram here, where it's labeled sand boils, that's referring to this sediment that comes kind of pouring out onto the surface there. Here's another video of liquefaction from the earthquake that occurred in Indonesia in 2018. And in this case, we had liquefaction that occurred on a relatively steep slope. So once the ground started acting like a liquid, instead of just things kind of bobbing around, they actually flowed downhill in a big mud flow, basically. So here we can see, entire houses that are being carried along. I'll mute this. Being carried along in these mud flows that occurred due to liquefaction. So on the video, it also has some captions of someone talking about what happened during this event. And so as you can imagine, if the ground becomes liquid, in addition to these the flows we saw here, even if things aren't carried away by the movement of the liquefied ground, it's certainly easier for buildings to collapse and things like that. Okay. Any questions about liquefaction? So in terms of thinking about the geological conditions that are going to result in liquefaction, this occurs where you have saturated sediment, right? So generally places that are close to water are more likely to have saturated sediment, and you might be concerned about liquefaction in those types of settings. Or even if it's not close to a body of water, if there's sediment and there's groundwater there, you can have liquefaction happening. Okay. Another hazard that can be triggered by shaking is landslides. So in this case, we're going to be concerned about landslides anytime that we have relatively steep slopes, steep topography, in a place that has earthquakes, right? So generally, a landslide occurs when you have a steep slope that the basically steepness of the slope and the gravitational force pulling down on the steep slope exceeds the strength of the rock or the cohesion of that material. So shaking from earthquake can cause that slope to fail and produce an earthquake. And there's also other things that reduce the cohesion of that material can also contribute to landslides, right? So if you've had a lot of rainfall recently, and there's water within the rocks and the sediments on the slope, that makes those rocks weaker and more likely to fail, right? So if you have a combination of rain and an earthquake, you have steep slopes, it can be bad for landslides. Additionally, if you have loss of vegetation, especially after a fire, that can also make slopes more susceptible to landslides. Okay, so generally, yeah, we have steep topography, earthquakes, we should be concerned about landslides. So this, these pictures are showing a huge number of landslides that occurred in Nepal after the earthquake there in 2015. So on the map, each of these red dots, I believe, is a mapped landslide that occurred after this magnitude 7.8 earthquake, as well as the aftershocks related to that. And there were thousands of these landslides because this is in the Himalaya. And as you can see from these photographs, very steep slopes that are pretty much ready to fail if there's an earthquake. And so these landslides also ended up killing hundreds of people because there was these villages that are right up against these very steep slopes. And so in this case, there was a landslide that actually basically wiped this entire village out. You can see you can't even see any of the structures after that. So there's in the chat, Rachel shared an article that talks about landslide risk in California, right? A place where you have steep slopes, you have fires that are destabilizing the slopes, and you can have earthquakes and very intense rainfall in the winter. They get these big storms that sometimes cause landslides. So that's thanks for sharing that in the chat. Okay. And then another hazard we can think about that's triggered by an earthquake is tsunami. So in this case, it's not the shaking that triggers the tsunami, but rather displacement of the sea floor. So if we have a fault that's underwater and that fault has vertical displacement on the fault, so reverse fault, thrust fault, or a normal fault, usually not a strike slip fault. So if we have, in this picture, we have a subduction zone. So this is a thrust fault that when that earthquake happens, the hanging wall suddenly moves up. So the sea floor moves upward and displaces the entire column of water, right? Then that displaced column of water collapses basically and moves outward, like big ripples, kind of like throwing a rock into a pond. It can travel really long distances. So a few ways that these tsunami waves are different than kind of the typical wind-blown waves you see on the ocean is that, one, they have a much longer wavelength. So tens to hundreds of kilometers as opposed to like tens of meters for a wind-driven wave. So what that means is that, you know, as the crest of the tsunami comes in, right, the water level is higher, and then you have the trough of the wave, the water level is lower. But so that crest is very long, and so the water comes in and it keeps coming in for a long time before it goes out again. It doesn't just come in and go back out like a normal wave. These tsunami waves also travel very quickly, right? And so you have both this wave that's coming in for a long time and it's moving very fast, so it has a lot of momentum and it can do a lot of damage. When you see these waves out in the open ocean, the amplitude of the wave, so how, if you're in a boat, how much your boat would bob up and down as a tsunami wave passed under you would be relatively small. But when the waves reach shallower water, they slow down. And just like our amplification of seismic waves, when they slow down, the amplitude gets bigger. The same thing happens with tsunami waves. So when they reach the shore and they slow down, that amplitude can get really, really tall, right? So you have this really high wall of water that's coming in really fast and keeps coming in for a long time and can travel a long distance inland and cause a lot of damage because of that, right? Okay. Any questions about tsunami?
I have one question. So like the diagram here has like a continental and then like an oceanic. Do they ever like form with two like oceanic plates?
Yeah, you could have a tsunami. It could be two oceanic plates, as long as if you have subduction happening. Yeah. Okay. So in addition to these, natural hazards associated with the earthquake, there's secondary hazards related to how these earthquakes interact with the human system and infrastructure, right? So the shaking or ground rupture can cause ruptured gas lines or ruptured water lines that cause fire and flooding. You can have damage to nuclear reactors, as we saw with the Fukushima in Japan in 2011. And often looking at longer term effects, right? After the earthquake, if there's damage to infrastructure, a lack of clean drinking water and sanitation, that can lead to disease outbreaks, right? So if we think about the earthquake that happened in Haiti in 2010, there was a lot of damage there from the earthquake itself. A lot of buildings collapsed and people were killed by that. But there were even more people that were killed by disease. There was a big cholera outbreak that happened after the earthquake. So that can be a big factor as well. Okay. So let's do a poll everywhere question to think about which of these hazards would be of most concern in a particular location. So in this case, we're thinking about the San Andreas Fault running through San Francisco. And so San Francisco, as you know, is on the San Francisco Bay. There's a lot of low areas built on unconsolidated sediment. There's other areas of San Francisco that are very hilly, but specifically thinking about these areas that are built on this unconsolidated sediment, which of these hazards do you think residents of the area should be most worried about? Surface rupture, liquefaction, landslides, or tsunami? Okay, so it looks like most people have answered the poll. So I'll go ahead and look at the responses. And yeah, 67% of people said what I would consider to be the most concerning hazard for these particular areas is liquefaction. If you have unconsolidated sediment that might be saturated with water, once you shake that, it can liquefy, and that can cause a lot of building damage, even in areas where you have strong building codes. It's hard to build a building to withstand the ground going completely liquid underneath it, right? Surface rupture would be of concern to someone who happens to live right on top of the fault, but most people are going to live a little farther away from the fault and probably won't get direct damage that way. And again, landslides be of concern for areas that have steep slopes, but not so much for these people living in these low areas on unconsolidated sediment. And tsunami would be of very little concern, partly because this is a strike-slip fault, right? So even people that are close to the water, strike-slip faults are unlikely to produce a tsunami. If it was a thrust fault, then I might, rank that as being a little bit more of a concern. Okay. So this is the question from the exercise that I said you didn't have to do, right? So what we'll do is talk about this in breakout rooms, right? And do it as a little activity in class, right? So Let me open up the Google Docs. I'll paste the link into the chat. So what we have is a one slide for each group. So your group number will find the slide that's the number of your group. And there's a map here that shows a map of the Seattle area, right? So here's downtown Seattle, the industrial district, some other communities in the general area around Puget Sound shoreline. So we're going to look at these three: shoreline, downtown Seattle, and the industrial district, and think about for each location which hazard you should be most concerned, right? So there's a legend on the map that shows these red lines are faults, right? And these are mostly shallow, as it says, shallow thrust faults that can produce pretty large earthquakes, magnitude 7. The pink areas are showing where we have steep slopes. The hatchered area is water saturated sediment, and the blue is water, right? So each group designates someone as the note taker reporter for the group. You can type in your group's answer to this question, and also put in the notes, the names of the students participating in your breakout room. So let's see, I think we'll do about 6 minutes in the breakout room. Does anyone have any questions before I put you into breakout rooms? Okay. And if you have a question, you can always use the ask for help button and call me into your room. Okay, so everyone's on their way back from the breakout rooms now. So what we'll do now is we'll just talk about each of these different locations, and I'll ask for someone to share their group's ideas about what would be the most important hazards at each of these locations. Right. So we'll start with shoreline. Is there anyone that would like to share what their group discussed about the shoreline community and the hazards there? Logan?
We said that there would be landslides because of the steep slopes in the area, and because it's on the coast, tsunamis might be an issue as well.
Yeah, so it just got very dark at my house. I'm going to turn on the light. Yeah, so exactly right. I would say that landslides would be a big concern. So you can see that the community itself is in this area that has a lot of steep slopes. Possibly tsunami, depending on, we might need to know a little bit more about the topography of this area. It looks like they're a little bit removed from the coast itself, and given the steep slopes, they're probably at a high enough elevation that the tsunami would probably be safe from a tsunami. But if parts of the community are closer to the actual sea level, then they would definitely be concerned about tsunami there. Does anyone have anything else to add about shoreline? Those are as I said, the main thing I would be concerned about there is the landslides. Okay, what about downtown Seattle? Bianca?
Our group said that because of the like unreinforced brick buildings, that ground shaking is probably going to be the biggest concern, just because it would threaten collapse.
Yeah, I would agree with that for sure. Yep. Emily, did you have something to add?
We said, oops, wait, where'd it go? Liquefaction, because there was a lot of water saturated sediment in the area. So that could be an issue as well, especially with the buildings.
Yeah, possibly. I think on the map, it's a little hard to see the pattern. The quality of the image isn't perfect. You're mostly seeing roads. I'm not sure how much of that water saturated sediment is in the actual downtown area. There's definitely some on the edges of the downtown area. So in the parts of downtown that have that water saturated sediment, that would be another concern there. Anything else people thought for downtown Seattle? I would say probably also tsunami would be something to be concerned about, since it does come right up to the coast, and these are thrust faults, so there's a potential for them to generate a tsunami there. Okay, and then the last one, the industrial district. What did people think about in terms of the hazards in the industrial district? Haley?
You said liquefaction because of all of the water saturated sediment and also surface rupture and ground shaking, since it's like right through all the fault zones.
Right. Yeah, so definitely there's a lot of water saturated sediment. And as it says, it's actually built upon former mud flats that were filled in. So a lot of this artificial fill is very susceptible to liquefaction. And then for people that or structures that are located right on top of these faults that go through here, surface rupture to be a concern then. But I would say that probably the larger concern is the liquefaction that's going to affect a much broader scale. And did anyone have anything else to add for the industrial district? No? Okay, again, this would be another one where you might, depending where you are exactly, tsunami could be a hazard, probably less so than downtown Seattle, because most of it's a little more inland along this little river here. And I think I saw on some of the notes on the slides, at least one group was thinking about secondary hazards, right? So depending on what kind of industry is in this area, you might be concerned about potential damage to things in that area, but toxic releases, things like that. So it's a nice kind of extra thing for people to be thinking about. But again, the biggest one here is probably the liquefaction. Okay, so that wraps up our unit on crustal deformation and earthquakes. And as a reminder, this is included on the exam that you have next week. So if you have any questions about any of these learning objectives, either what we talked about today or something from last week, now would be a good time to ask questions. Are there any questions? Yeah, Orion?
Since the test is open book, are the questions going to be like more difficult or?
Yes, I mean yeah. So I try to avoid questions that are simple recall and have a little bit more of application, but it's not going to be like a lot more difficult, right? So in general, I think this exam being open book would be easier than the closed book exam I might give under different circumstances, if that makes sense. So I will say that there's a practice exam on Blackboard, and that will give you a really good idea of the types of questions that I ask. Obviously, the actual questions on the exam will be different, but in terms of the difficulty of the questions and the style of the questions, they'll be quite similar to the practice exam. Okay, are there any other questions about earthquakes? So what we'll do now is we'll take a 3-minute break, and then after that break, I'll talk a little bit about the exam. So if there's questions about the exam, we'll address that now. But if there's any questions about earthquakes or crustal deformation, I can answer those now. I can also answer questions about that after the break, but I'm not seeing more questions. Okay, so let's take a 3-minute break, and then I'll talk a little bit about the exam after that break. Okay, so we can come back from our break. So as I said, I've put a bunch of information on Blackboard about the exam next week, as well as materials to help you study for the exam. And so most of this information is in the weekly folder for this week. So one of the things that you're doing this week is studying for the exam, right? So I have general information about the exam. including the exam format. So basically, I will make available a few days early, so it'll probably be next Sunday. I'll make available the answer sheet, and then the questions I'll post on Blackboard during the exam time, which will be in class that Wednesday. And then once you fill in your answer sheet, you're going to submit that as a PDF to Gradescope, right? And so I've said here, I suggest printing out that answer sheet ahead of time, writing your answers, scanning it, uploading it. Just because personally, I'm always paranoid about something going wrong and losing my work when I'm working on the computer. You do have the option of using a PDF editor. But again, if something goes wrong and you lose your work, that's not great. And also, you might have to label things or make sketches that you want to make sure that you have a PDF editor where you can do that and you know how to do that and you've practiced doing that. So I have the practice exam is in the same format as the actual exam, where you have an answer sheet and the questions are separate on Blackboard. So you can practice doing that and seeing what works better for you, whether it's printing out and doing it on paper or using a PDF editor. So the exam itself, as I said, will be in class. I'm going to try to make the number of questions, the length of the exam be such that you should be able to get through it in about an hour. And then you have that extra time to, if you need to scan and upload to Gradescope, that it's not too stressful. Okay, so that's the information about the exam there. And then I have some, tips for studying for the exam, right? So you should focus on the learning objectives for each unit. And those, again, are in the PowerPoint slides at the beginning and kind of scattered throughout each of the PowerPoint slides, but I've also put them all into a single Google Doc here where you have the learning objectives plus some vocabulary to make sure that you're comfortable using that vocabulary. Oh, this is the wrong link though. This is fall 2020. I'll update the link on Blackboard. They're pretty much the same. You can also get to that link through where it says study guides. And unit learning objectives. This should be the correct link, right? Spring 2021. So I'll fix the link in the weekly folder. I'll do that right after class. Okay, let me go back to the weekly folder, right? So there's the unit learning objectives. And as I said, you might want to look at the practice exam to get an idea of how I actually test you on the learning objectives to help guide your studying. And you can also look at the exercises on Gradescope, right? Those have the rubric that show kind of how points were awarded and lets you see where you might have missed points. And I haven't posted these yet, but I'll have a link here to all the past Poll Everywhere questions that you could use those as a way of testing yourself as well. And then at the bottom here is the actual practice exam, right? So if you click on this, there's an answer sheet, right? So here's the answer sheet you can fill in, and then the practice exam questions. And so if you submit your completed practice exam to Gradescope by Sunday, you can get 2% extra credit added to your exam. You could also just, do this, don't do the entire thing and don't submit it, and it's good practice, but you won't get that 2% extra credit. And then after Sunday, I'll post the answer key to the practice exam so you can check your answers against the answer key. I think that's the main things I wanted to point out there. And again, as you're studying, another place you can go is study guides, right? It's a lot of the same things that I have in the weekly folder. Here's the unit learning objectives, Poll Everywhere questions, a link to the practice exam folder. And I've also posted this strategies for effective learning that from this website called the Learning Scientists. And there's these different practices and some tips for how to implement that. Okay, so I see a few questions in the chat asking, is the practice test about the same length we should expect for the exam? I would say yes. When I do the practice exam, I'm a little less careful about thinking about exactly how long it is. So sometimes I'm like, oh, I should give them an extra question. It might be a little bit longer or shorter than the actual exam, but it should be about the same length. Meaning it should take about 60 minutes. If you find that the practice exam takes a lot longer than that, send me an email and let me know so that I'm like, when I'm finalizing the actual exam, I'm aware that maybe the practice exam took longer than I intended. Another question, do we have any other exercises to do before Sunday? No, so there's no exercise this week, just studying however is best for you to study. And if you want that 2% extra credit, doing the practice exam and submitting that on grade scope. Yes, and then there's another question that says, will the Zoom room be open for questions during the exam? Yes, so if we look in the weekly folder for this week, where it says under information about the exam next week, exam policies, I am encouraging you to join our Zoom meeting during that time, because if you have questions, you can type questions into the chat. If there's something on the exam that needs clarification, I have a typo or something, I'll make an announcement in the Zoom meeting to let people know that, and also be reminding people how much time is left to take the exam. Everyone can have their videos off. This isn't the purpose of joining the Zoom meeting, isn't for me to watch you and make sure you're not somehow cheating. The purpose is to make it easy to ask questions. Okay. Any other questions about the exam or the practice exam or studying for the exam? Yeah, Bianca.
I'm just a little bit confused about the format. So are we printing something out, then writing on that, and then scanning it in, and that's the test?
Yeah, that's what I would recommend doing. There's a PDF that you could fill in with a PDF editor, but I think it's because you're going to have the questions up on your computer screen, and you're going to have the Zoom meeting open, and I find it tends to be a lot to be trying to do all of that on the computer. And like I said, I'm personally paranoid about my work not getting saved, and in a timed exam situation, I just wouldn't want to deal with that. But you could do it with a PDF editor. I would recommend printing it out ahead of time and scanning it.
Okay, perfect. Thank you.
Yeah. Any other questions? The other thing I'll say is that we'll take some time in class. So the exam is on Wednesday. So we'll take some time in class on Monday, have an opportunity for people to ask questions, go over concepts or particular questions from the practice exam or from the exercises, just to review a little bit for the exam in class on Monday. It won't be the whole class. It will probably be about 20 minutes or so to review in class. So you might want to come to class with questions. But I think that's mainly it. Given that we only have 7 minutes left in class, rather than starting on rocks and minerals, we'll just save that for next class. So if there's more questions, you can ask more questions. Otherwise, I think we'll finish early today. As I said, I'm giving you the day off on Wednesday, because Thursday is a spring break day. My other section has no class on Thursday, so I thought it made sense just to keep the classes in sync and give you guys a little bit of a break. I feel like we've been going pretty fast paced the last couple of weeks, and it's nice to have a little extra time to study too. So that's it. We'll finish about 5 minutes early today, but I'll stick around if you have any other questions.